Have you ever driven past a massive oil refinery, with all its pipes and towers, and just wondered, how does all of that work without blowing up? Or how does the power grid keep everything perfectly balanced second by second? Well, there's an invisible orchestra at work, a really sophisticated system of automated controls that's conducting a symphony of flows, temperatures, and pressures. So how do they manage this incredibly complex world and keep it from descending into chaos? Okay, let's dive in and find out.
Here's our game plan. We'll start with the huge challenge that modern factories face. Then, we'll see how engineers actually describe this super dynamic world. After that, we'll uncover the elegant solution, the feedback loop. And finally, we'll get into the real art form, tuning these systems for perfect performance.
All right, first up, the big challenge. You see, modern industrial plants are just mind-bogglingly complex, and everything is interconnected. And they're constantly facing changes. The raw materials coming in are different, the weather outside changes, customer demand goes up and down. To keep things safe, high quality, and efficient, you need a control system that can think and react on the fly. You absolutely cannot just set it and forget it.
So that brings us right to the million-dollar question. With so much at stake, we're talking huge amounts of money, environmental safety, the quality of the final product. How do we keep these giant interconnected systems from just spiraling out of control? Well, the answer starts with really understanding the process itself.
The foundation of all of this, of all process control, is actually pretty simple. You can't control what you don't understand. So the very first step, always, is to identify the key variables. Let's call them the main players in the game.
First, we have the controlled variable, or CV for short. This is your main goal. It's the one thing you're trying to keep locked on to a specific target, what we call a set point. Just think about the thermostat in your house. The temperature you set it to, that's your controlled variable. That's the goal.
Next up is the manipulated variable, or MV. This is the knob you can actually turn, the lever you can pull to change your controlled variable. Sticking with our home heating example, this would be the furnace kicking on or the AC unit blowing cold air. It's the tool you use to hit your goal.
And finally, there's the disturbance variable, the DV. These are all the unpredictable things that are always trying to mess with your goal. They affect your system, but you have no direct control over them. For our thermostat, a disturbance could be someone opening a window or the sun suddenly blasting through the glass. This is your challenge.
Let's make this real with an industrial example. Imagine this blending process. Our goal, our controlled variable, is the final concentration of the product. Now, the tool we have to achieve that goal is the flow rate of one of the streams coming in. That's our manipulated variable. And the challenges, the disturbances, are the unpredictable changes in the other stream. And this is the key takeaway. You aren't controlling the concentration directly, you're controlling it by manipulating the flow.
So, we've identified the players. But how do they interact? How does turning that knob actually affect the goal, especially when all these challenges are popping up left and right? For that, engineers need a special language, a way to describe this constantly changing, dynamic world. Building a control system isn't just guesswork. It's a very structured engineering process. And as you can see here, a really critical early step is to develop a process model. This is basically a mathematical description of how the system behaves. It's the blueprint you absolutely need before you can even think about designing the controller.
Now, at the heart of that model is something called a transfer function. Don't let the name scare you. Think of it like a recipe. It's a mathematical way to describe the exact cause and effect relationship between an input, like turning a knob, and the output, like the final temperature. It lets engineers predict with incredible precision how the system will respond to any change they make.
And here's where it gets really clever. The physics behind how these systems work often involves some seriously complex calculus. But engineers have this mathematical shortcut that can transform those hairy differential equations into much simpler algebra. This is the magic that makes it possible to build these predictive models and design controllers that actually work in the real world.
Okay, so we've identified the variables, and we have a language to describe how they all relate to each other. Now it's time to bring in the hero of our story, the feedback control loop. This is the fundamental, super elegant concept that keeps all these complex systems in balance.
Now, there are two main ways to do this. Feed-forward control is predictive. It tries to see a disturbance coming and act before it causes a problem. The catch? It can't see everything. Feedback control, on the other hand, is reactive. It doesn't care what caused the problem, an open window, bad raw materials. It just measures the final result, the output, and corrects any error it finds. This amazing ability to handle the unexpected is exactly why it's the absolute workhorse of industrial control.
The entire feedback loop, as powerful as it is, can be boiled down to this simple, continuous cycle. First, you measure the variable you care about. Then, you compare that measurement to where you want it to be to find the error. And finally, you correct for that error by adjusting your tool, the manipulated variable. That's it. Measure, compare, correct, over and over again.
So, what's making the decision in that correct step? Well, in over 90% of industrial loops, it's something called a PID controller. This is the brain of the whole operation, and its name, PID, tells you exactly how it thinks about the error to figure out the best correction.
I love this way of thinking about it. The P for proportional looks at the present. It asks, how big is the error right now? And reacts proportionally. The bigger the error, the bigger the push. The I for integral looks at the past. It adds up all the past errors and says, hey, this error has been hanging around for a while. I need to push even harder to get rid of it for good. And the D, for derivative, looks to the future. It sees how fast the error is changing and says, well, I predict we're going to overshoot the target, so I'm going to ease off a little. It's this powerful combination of thinking about the present, the past, and the future that makes the PID controller so incredibly effective.
So, we have our controller, our brain. But just installing it is only half the battle. The real magic, the part that separates a good control system from a terrible one, is tuning it, customizing it to get the absolute best performance for that specific process.
So what does a good response actually look like? Well, imagine you change your target. You want the system to get to that new target quickly, right? But you don't want it to swing wildly past it. That's called overshoot. After that, you want it to stop bouncing around and just stabilize at the new target as fast as possible. The dream is a response that's fast, precise, and super stable.
And this really gets to the core challenge of tuning. It's a balancing act. It's a classic trade-off. If you tune the controller to be really aggressive, sure, you get a fast response, but the system might become unstable and oscillate like crazy. If you tune it to be too conservative, it's very stable, but it's so slow that it's basically useless. The real art is finding that perfect sweet spot right in the middle.
And that's because there is no single best setting that works for everything. Every single process has its own personality. Controlling the flow rate in a pipe is super fast, so it needs a quick, simple controller. Controlling the temperature in a giant tank is much slower, more gradual, so you can use a more sophisticated approach. Each one needs a totally different tuning strategy to work well.
I want you to let this sink in for a moment. This quote from the source material just highlights how absolutely critical this final step is. When something goes wrong in a plant, it's not always a broken valve or a faulty sensor. 4 out of 5 times, the problem is simply that the controller's tuning isn't right for the job anymore. Tuning is, well, it's pretty much everything.
So, there you have it. We've gone from the fundamental challenge of managing complexity to defining the key players to creating a language to model them, and finally to the feedback loop and the PID controller that brings it all home. The next time you use cruise control in your car, or just flip a light switch and rely on the power from the grid, maybe you'll see that invisible orchestra hard at work. What other automated systems will you now notice conducting the world all around you?